So please keep that in mind.
Welcome to episode 3 of ConNext Season 2. For those who were not here last year or at the last session, here's a short introduction of how ConNext came into being and what we are trying to achieve. ConNext is a joint effort of the conservation training programs of the universities of Antwerp, Amsterdam, Hildesheim, Cologne, Potsdam, Westin, Thomas and Lincoln, all within the field of wood and furniture conservation. Some programs also incorporate polychromy and modern materials. You will hence encounter a wide range of subjects throughout the different ConNext sessions. Our ambition is to connect you, the students, with your international student colleagues and to give you the opportunity to share your work. Education is paramount for the future of our field, and it starts with sharing. Sharing your hard work, your experiences and knowledge. ConNext tries to provide a platform for this exchange. We also hope that you will continue sharing for the remainder of your studies and your professional life. As the ConNext team, we hope to lower the threshold to send in your work for conferences like those of ICOMCC, Ebenist or Future Talks. So let ConNext be a kickstart for your national and international career and networking. And international it is. Last year, we had 186 registered participants, that is 214 overall for all ConNext sessions, united from over 28 different educational and research institutes and from 16 different countries. That's better than we have ever expected. We think by now you are excited as we are to kick off this third ConNext session with the help of one of the many established keynote speakers who were so kind to share their knowledge in this event. So let's ConNext.
Thank you, Henning. Yes, it's my great honor to introduce today's keynote speaker, Erma Hermens. Erma is the director of the Hamilton Kerr Institute for Conservation and Heritage Science, with a team of 15 conservators covering paintings conservation, paper, book, illuminated manuscripts and objects conservation, as well as science. The Hamilton Kerr is a department of the Fitzwilliam Museum at the University of Cambridge. Erma is also a professor in technical art history at the University of Cambridge. Before that, she occupied the Rijksmuseum chair in conservation practice and technical art history, University of Amsterdam, and was senior researcher at the Rijksmuseum. After 9 years as senior lecturer at Glasgow University, where she established the first international master's program in technical art history. Erma, thank you for being with us, and the floor is yours.
Thank you very much for your kind introduction and for the invitation to speak. That's very nice to do. I must say I spent 7 hours today traveling from Amsterdam to Stansted Airport and back to Cambridge, which was not what I wanted to do. So the sun is shining here now, so that's at least a good thing. So welcome everybody. I'm going to give a short talk about technical art history with a few examples. Of course, I can talk for hours and hours about this, so I do hope that I can explain what, for me, technical art history means. It's sort of deconstructing and reconstructing the act of making. It's what we often say, and I want to give you some examples. So to begin with, there's a quote here from David Bomford in a book that we published quite some time ago, but it is still really valid, I think, and it really captures the essence of it. So I will just quickly read it because it introduces basically what I'm going to do. So at least imaginative, technical art history is a form of deconstruction. The work of art becomes a material text to be dismantled in isolation, human authorship denied, or at least irrelevant. But at its best, it underwrites everything. It travels in a great sweep from the general to the particular, from global sources of pigment supply to the specifics of extracting dyestuffs in 17th century Holland, from medieval concepts of color to vivid glimpses in London studios. It is impossible to understand art properly without its insights. It acknowledges, celebrates the artist at work and the act of making. I think this sort of captures the essence of it. So central for technical art history is indeed the act of making. And with that in mind, you know, we're trying to understand a maker and the whole process of thinking and making the materials, understanding materials, and so on. As every maker makes thousands of decisions during the process. What is he or she using? This connection between head and hand, mind and hand. So an intuitive connection that can only be forged in specific situations or locations. Skills, tools, dexterity, tacit knowledge building, the setup or the layout of the workshop and the choreography of the making process. All these things are part of that making process that in the end creates the objects we are all as conservators working on and as researchers investigating. So it's all about places, about people and stuff, really, you know, what is happening here. The methodology that we of technical art history is a very interdisciplinary one, but basically the questions that we ask are maybe, you know, rooted in a very old way of doing research. It comes from Aristotle, who said, for in acts we must take note of who did it, by what aids or instruments he did it with, what did he, where he did it, why he did it, how and when he did it. That sounds a lot of different things, but the questions what, where, why, who, when, and how are at the core of technical art history. And I think that that is really important to keep in mind, because often some of these questions, for example, in pure art historical research, are not asked. And so there's a shift of focus here towards that making, that material, that how was it done, with what, and why was it made, and with certain methods and materials. All these questions need to be at the core of what we're doing. So the object is at the center of technical art history. So I would say that it is very object-led, not just object-based, but object-led. So the object creates the questions. And around all of that, we can place different methods. So art historical research, material culture, for example, history of science, art technological sources, so recipes for making, etc., scientific analysis, and reconstructions. And of course, conservation is part of all of this. Then, of course, we need to think about anthropology of making, practitioners, artists who are working now, who have a lot of material knowledge that we need to really tap into. And then you have all these contextual things, the history of trade in materials, economics, etc. There was just a conference in Amsterdam about wood, from forest to cultural heritage. And I think that also showed so much how important that context is for understanding practices, objects, how they look, what their lives have been really, and then as a conservator, how you can be confronted with all these things and how to try and get insights in that. And technical art history is a method that can be very useful for that. A new, well, relatively new part that we now should include is digital humanities. A lot of digital imaging, digital research methods, etc. Are more and more used also within conservation and also within technical art history. So data collecting is what we're doing as technical art historians or technical researchers. So it's all based in this interdisciplinarity idea. So art history, purely technical art history, conservation, natural sciences, social sciences, digital humanities, art technological text analysis, artists, etc., more and more and more. So this leads to what we would call hybrid data. And the synergy of all these data is often seen as technical art history. It's really at the core teamwork. It only works with a team of researchers. So I'll come back to that later on. So to illustrate this, I would like to give you a couple of examples that I worked on with a group of master students in technical art history at the University of Amsterdam. And one of the examples is this object, is St. George and the dragon. It's in the Rijksmuseum collection and the collection of the Amsterdam Museum, so joint, and not much is known about it. And here you see a better image. So this is the statue. It's about 1.60 meters high. And then there is a loose foot, a pedestal that should probably be underneath here. And then there's lots of bits and pieces, loose bits and pieces. So just during the second lockdown, we managed to, with this small group of students, 4 of them, to examine George. It became the George project, and try to understand if we could place it in time, in techniques. Why does it look the way it looks? How was it made? What was it made for? And so we went through all these questions, including also a technical analysis of the surface layers, trying to understand how this connects to that, and where all these pieces belong to. And it was, again, teamwork. So we worked with, amongst others, Paul van Duin. You probably already heard him speak, head of furniture conservation in the Rijksmuseum, the dendrochronologist Marta Dominguez, to try and identify the wood. And these are 2 of my students who were doing, who were registering, documenting the sculpture with 3D scanning. So this is an Artex Spider scanner to create a 3D model for research, and also for this dissemination, to show to a public, to an audience, what the whole research is about, and to be able to see the object in 3 dimensions. Here you see some attempts to link the object with that pedestal, and there's it's St. George and the dragon. So the dragon tail, you see here part of it, and then it goes around the leg of St. George. Very difficult to understand how it all would fit together, and we suspected quickly that this pedestal was added later. We discussed this with Michele Magoli from New York Institute of Fine Arts, who examined a similar kind of construction of a foot made in this way. So that was one strand of research we have followed up on. This is a very old photograph of the statue. So then you see there's a spare, and the foot is connected. So that helped us to understand all these loose parts. We found all kinds of traces of techniques, for example, applying some kind of textile before applying surface layers, something that you find often in polychrome sculpture, but also on panel paintings from the Renaissance. So the sculpture probably late 15th century, but that is still a question mark. But you see different weaves, and also that already indicates maybe different treatments. Some could be original, some could be added much later, maybe also conservation treatments. We X-rayed the sculpture, and this is the face, and you see here also the face, the eye, nose, and a join here. So the hair seemed to have been attached. Very peculiar. This is the tail around the leg, and we found different kinds of nails in the X-ray. Here a very modern screw, so that is a very different kind of thing. So all these things have been documented and helped us to understand better what we were looking at. So here you see again the scanning. We did also take cross sections. We found very different things, so gesso layers, gypsum, so no chalk. So is it a German sculpture, Southern Tyrol? That was the idea. Or should we look elsewhere? This is still ongoing because it's an incredibly rich object, and the description of it having been polychromed in color, and we found little bits of color that no longer are surfing, you know, because as you can see, it's largely a reddish tone and a lot of gilding, which is very damaged. So trying to unravel how this sculpture should at least be fitted together was quite complicated. But with the 3D scanning, and we made a little film reconstruction that I hope Sophie is going to show us now. You can sort of see how it all comes together. The tongue in the dragon, these pieces that go the front of the shoulders, and then the spear, and then you have the whole sculpture as far as what we have together, the fingers attached to it. Using these kind of methods, the reason I showed you this, because there might be a conservation treatment following, but it was very much a research project. But what I really wanted to show you is how using these 3D scanning methods, you can create wonderful outputs that are interesting also for museums to show, for the public to understand, etc. And this was done by the students' technical art history. And I think conservators are more and more engaging also with these kind of methods. I think it's really important that we come from behind the scenes, which is often said about what conservators do, to as front of house, if so to speak, and to show you, to show the public our research methods, but also, of course, conservation methods can be visualized, and etc. So this is a wonderful way of doing that. So what we're collecting within technical art history-led of object-led research is trying to unravel all the narratives that are in that object, hidden in the object. Led by this who, why, what, when, etc. So the stories of craft production, art production, the studio or non-studio environments, of the procurement, production, availability of materials, demand, market taste, of commodities and status, of creators, workshops, assistants, and apprentices, knowledge exchange and collaboration, function and meaning of written testimonies, and from scientific developments, from alchemy to nano, and so on. So there's a lot of things from narratives in the object and narratives from our treatments and our research as well. To just give you an impression of another piece of research in that sense, this is a simplicity cabinet or collector's cabinet from 1730 in the Rijksmuseum. It's a mini pharmacy. Here is the top here is slightly closer up. All the little pots and every object here contains something. That could be herbs, that could be spices, could be materials with medicinal qualities. And this is the little painting here of the pharmacist looking at a glass bottle. And in the lower part of the cabinet are drawers with all kinds of objects, and they're fantastic. Such a rich object. So it's for so many reasons interesting. However, one of the drawers contains this small selection of pieces of what looks like, difficult to say, but it is actually glass. So it's a raw material, and here you see some of them slightly bigger. This is sort of charts of a round glass cake. So you can see here round line, because in the middle you would see a stamp of whoever made this. These were made in Murano in Italy by a firm Miotti, and Miotti existed in the late 16th century up until the 18th century. And this is Latimo, that's white glass, and with the stamp of Miotto, but you see only parts, it's a fragment. Here you see another one with a stamp. This is looking black, but it's actually a blue smalt glass, copper base. I see nice questions going by. I'll answer them later. And so on. And so we were specifically interested in the smalt, the blue glasses, and then we started investigating. So this is where we started, this fragment of blue glass made in Murano, and used these glass cakes by mostly, as far as we knew, by enamelers. So you would grind pieces of fragments of these glass cakes very fine and mix them with a binding medium and put them on your copper plate where you wanted to enamel, and then melt it in the oven, in a kiln, sorry. But when we started looking into that, some of these pigments, some of these fragments, like the yellow ones, turned out to be very similar in composition of some pigments used by painters, as did the smalt, the blue glass cakes as well. So then once you start looking, then Miotti at the center, that's these fragments. You go to Vende Colori, who in Venice, who sold pigments and materials for enamelers. The enamelers had an impact on Limoges, so these glass cakes also were exported. They're called smalti. Glass painters used them, painted on glass. Murano is important. Blue glass in Venice, treatises, pigment trade, the mines in the Erzgebirge in Germany, where the cobalt ore comes from, which was treated, and then it's called sapphire. Sapphire was used to make smalt. Sapphire was also used for the Dutch smalt industry. The Latin yellow, that's what you see here, also was used by potters, and so on. So this is a slightly messy sort of diagram, but if you can make it even fuller and even more organized, and it's amazing how you get all these intersecting narratives. So that's really what technical art history is about. So you have your object at the center, and you look at the making, the concepts behind it, the context in which it was made. That feeds all into a material history, that are these intersecting narratives. Also intangible heritage, so testimonies, written documents, all kinds of tools, materials, oral history, etc. And that also feeds into object biographies or itineraries. We started very much using this biography idea, the life of an object from the birth, the making, to how it is now. But and that's a concept that comes from anthropology and an ethnographical approach. But there's a very interesting switch now to itineraries, which do not necessarily have a very sharp beginning and an end. So it's continuing, and it's it's leading, going to lots of places. It has actors, movements, etc. It could be global and so on. So very, very nice way of interpretation from a piece of object-led research. Very important to mention is treatises and recipe books, and there are so many different kinds, different uses for all the disciplines, all the artisanal disciplines, so as much on furniture making and marqueterie and you name it, as well as on paints, glass making and so on. It's an incredibly rich resource. And just to show a very curious one that was bought by the Rijksmuseum a couple of years ago, the Théâtre de l'Art des Charpentiers, the woodworkers' theater of art, that has all kinds of things from keys and locks to automatons, furniture with contraptions in it, etc. But also models for chairs, etc. and so on, for very, very fascinating. So that is also a very rich source of information that we, as a technical art historian, should take into account. Very important testimonies. We can use those kind of testimonies and all that research and analysis of materials to inform reconstructions, remaking, or a reenactment, if you like, where you create this way of working in a studio and recreate it. Trying to understand that and create a kind of script. Why do we do that? Because we try to understand what is the general, approach of a method, a technique in a certain time. Are there anomalies or idiosyncrasies that indicate a certain maker, for example, or a certain region? Is there a lot of tacit knowledge and secrets that we try to unravel? Then we look at material affordances and constraints. So some things you can do with a material, or a material really helps you to develop a certain technique because it allows it. It can do that. You can do that with that material. But there are also constraints, certain things you can't. So you need to find other solutions. So all these things, when you reconstruct old recipes, for example, often become more and more clear because you find the problems and the gaps in our knowledge and so on. So remaking and reenacting is really, really important for technical art history. And if you don't know the project, I could really advise to have a look at the Making and Knowing project from Columbia University, which is on a treatise with all kinds of recipes, including working with wood and other materials. And they reconstructed so many of them. It's a fabulous website. If you don't know it yet, please do visit it because it's really, really fantastic. Well, to finish with the last example, I'm going to talk about turtles because after my talk, there will be two lovely talks about turtle shell use, and I'm really looking forward to those because during the lockdown, I got into a project with students that we had to do all online, and it concerns this big turtle shell. It's about 114 centimeters across, and it's painted with a portrait of Prince Frederick Hendrik of Orange on horseback. So normally in technical art history, object-led research, we would start with analysis, technical analysis of the object. Of course, during the lockdown, we were, as you all very well know, we were all sitting at home. So this was all done online. So we turned it around. We first did all the contextual research, conceptual research, and then we were going to go to the making as soon as we would have access to the object. Well, that last bit is still slightly in progress, but some of it I can show you. Here you see some paint losses, so you can see the beautiful turtle shell. This is on the inside, where you can see the ribs. Very fascinating to understand how turtles are, let's say, constructed. So we made study of all these different things. You see here also the art historical history, of course. There are many prints of the same scene. So clearly whoever painted this must have known these prints and used them as an example. But why on earth would you paint this on a big sea turtle shell? Lots of stories came out of that, and I will tell you where you can read them. But one of the things that we are now planning is DNA research of the shields. And actually, there are 2 more shields in the Rijksmuseum, one painted with a coat of arms and one unpainted. And we have some shields, found some shields in other collections. So we want to try and do DNA research, not ourselves, but here we get this team building. So we have contact with marine biologists and then especially people who specialize in DNA research, and especially ancient DNA, because this is supposed to be 400-year-old DNA, as the shield dates from 1631 approximately. It's a specific kind of sea turtle, the green sea turtle, where a lot of DNA is known, and it indicates where exactly these turtle shields, where the real turtles lived, and that gives us insight into trade routes, etc. So that's really fascinating way. There we collected lots of images of sea turtle hunts. Here you see that it's a Philips Gall engraving from the late 16th, early 17th century, and there is a lot more of this kind of material, really fascinating. There are text descriptions in all kinds of documents where they explain, you know, how they are found, how they look, and why they were interesting. This is from 1680. It says, in America there are 4 sea turtles. The first are big, weigh 3,000 to 4,000 pounds. Well, that's not quite right, is it? They lack a hard shell such that one can cut in it with a knife, are full of tran, oil, and are unsuitable to eat. The second are the green sea turtles of moderate size, with examples of 4 foot wide. Their skin is harder, covered by a small shell, as thick as horn, from which one makes lanterns. So this little fragment gives us already a lot of information also about making and use and kinds. So this kind of documents is very interesting for technical research and technical art historical research. We find the turtle shell, these big shells, in chambers of curiosities, in Kunstkammer cabinets, like the very famous one of the cabinet of Ole Worm. You see here 2 of these big shields on the wall, and there's many more that can be added to that. And we also found, for example, another one that was painted, and that is in the Kunsthistorische Museum in Vienna. It's dated 1510, so this is quite early, Italian. And here you see that the depiction derives from Livy's History of Rome, one of the ancient writers, circa 332 BC. And it's the battle between the Romans and the Gauls. And this is, of course, also a fantastic storyline for our shields, because Prince Frederick Hendrik was a very important military man, and maybe the shield has something to do with a military history. Well, for example, the military tactics of the tortoise, the attack, and the hare, rapid withdrawal, were already described by Livy. He wrote about that, Plutarch and Tacitus as well. And here you see Asterix and Obelix, a beautiful representation of the tortoise. So this whole military storyline is really fascinating for our shield. And in Konrad Gessner, in his Historia Animalium from the 16th century, writes about it and says it's not without great cost that this shell is called scutum, and the beast scutellaria, for when there is no buckler and shield so hard and so strong as this is. And Palladius was not deceived when he wrote thereof that upon the same might safely pass over a cartwheel, the cart being loaded. So this indicates the strength of this shield, and it's used for military action. Nice connection with Prince Frederick Hendrik in terms of concept, right, and context as well. So there's many more stories to tell. So how do we get from, well, this is where we started. And then we looked into the hunt. We looked into the stories about it. And the fragment that I showed you came from a book that was written by natural scientists, early modern scientists, who would travel on board of pirate ships. And here you have Blackbeard, one of the very famous pirates, and they wrote books about piracy, but included big fragments about nature, including about these turtles. So fantastic material and great fun as well to read these stories. Then it became a culinary specialty, because first it was used to feed the ships that were going to the South Americas and back, and it would give a lot of food. One sea turtle, 200 pounds or kilos of meat. And then they started to keep the shields, because first they threw them overboard, but then they became curiosities, as we've seen them in those chambers of curiosities. But then also they started to elaborate the material to use it in beautiful objects, and these precious and rare objects. This session is about, here you see a detail from the doll's house of Petronella Ordinem in the Rijksmuseum, and the whole exterior is covered with turtle shell and inlaid with metal. The culinary story is super fun and really interesting, but it all feeds in, you know, understanding the material. And then of course now we have the green sea turtle as an endangered species. So that is another interesting story. What we did with all of this is the students wrote blog posts about it, which you can find on a blog, looking through art blog.wordpress.com. So looking through art blog, one word. There's all kinds of things on there about conservation and technical art history, but there's a set of stories about the sea turtles. Now we are looking into cross sections of the paint layers and trying to understand how the turtle shell was prepared to serve, you know, as a support for a painting, and so on and so on. So all these things are now coming together, and the research team that we actually use for this project are technical art historians, historians, I should say, heritage scientists, a historian of science, natural history, military history, marine zoologists, genetics, animal biology, and then so it goes on. Going back to that image that I showed you at the very beginning. So that is really, in a very small, quick nutshell, some ideas on what is technical art history. Very important, interdisciplinary, working with all kinds of expertise, professionals, and the conservator, for me, plays a crucial central role, because conservators deal with the material part of objects very close closely and are connected to it, try to get more and more understanding of it. And that is an expertise that is crucial for technical art history. But the dialogue then taking from that object with all these other disciplines, also trans and cross-disciplinary, is actually fantastic, because it creates a whole new way of looking at objects. Often we start with an art historical question, but then involving all these different people, you get a very holistic approach and a very fantastic material story. It's about synergy, it's all about teamwork, it's a combination of expertise, but most of all, it's about communication and finding a common language, because it's not a field that is exclusive for one discipline. No, it's sort of a research arena where everybody comes together with the same motivation and the same interest, and then create this fantastic storyline. And that's me. Thank you very much for your attention. And well, I hope there's time for a few questions.
Erma, thank you so much for your inspiring keynote, putting the significance of object interpretation, the related research context, and the role of interdisciplinary collaboration so splendidly at the beginning of this session. So, as was indicated earlier, please put any questions for Erma in the chat for the Q&A session to follow after the next two talks. We are proud to announce now our first paper presentation of today by Alex Verlinden, who is a bachelor student from the University of Antwerp. Alex will talk about the identification of sea turtle shell used in the 17th and 18th century in Antwerp cabinets, which is indeed a truly rare and precious material. So Alex, the big screen is all yours.
Good evening, everyone. First of all, I want to thank Henning for the beautiful introduction. Today, I will be presenting to you an integrated method for identifying turtle shell. Integrated because a combination of different techniques and tools will be explored, in addition with basic knowledge of the material, in order to identify the material as correctly as possible. Identifying turtle shell is not as straightforward as one might think, and there are a lot of different factors into play which can influence the final determination. A basic understanding of the biological structure of the material is required, as well as an understanding of the historical use of this material and different imitation techniques that were present within the time period. And even then, it is not always possible to be 100% sure about the determination. The goal of this presentation is to provide you with the basic principles of turtle shell determination, meaning a basic understanding of the material, what signs you should look for, and which techniques can be used for identification should you ever encounter this material in an object. I will be talking about the use of turtle shell within cultural objects, the biological structure of the material, imitation techniques that were used within the time period, and finally, which techniques can be used for aiding in the determination. First of all, there is a lot of terminological confusion about the terms turtle shell and tortoise shell. Throughout history, it was common to refer to the material as tortoise shell, which is not taxonomically correct. The term tortoise actually refers to species which are predominantly land-based, whereas turtles spend most of their life in the ocean. Given that my research focuses on turtle shell inlay and veneer that originates from sea-based turtles, I will henceforth be referring to the material as turtle shell. When we talk about turtle shell in a cultural historical context, we are not referring to the shield as a whole, but actually the uppermost layer of the shell that is made up of keratin. This is a layer of a few millimeters thick, which, especially within sea turtle species, generates an exotic and aesthetically pleasing colored pattern. It consists of a multitude of transparent layers that grow seasonally on top of each other, creating a translucent, amber-colored material that is alternated by melanin-induced black spots. In order to use this material for the production of cultural objects, the uppermost layer is removed. Because turtle shell is a thermoplastic material, it is removed with the addition of heat, causing it to detach from the shell, resulting in several plates of a few millimeters thick. When removed from the shield, the translucent nature of turtle shell becomes visible. These plates are naturally convex shaped because of the shape of the shield, so they are subsequently flattened under pressure and heat, making it a workable surface. After this, turtle shell can be used as a decorative finishing material to decorate flat surfaces, or due to its thermoplastic properties, it can be molded and used onto complex three-dimensional surfaces, like this heart-shaped ornament right here. This versatility of the material opened up a myriad of possibilities to decorate decorative arts and make everyday utensils out of turtle shell, like frames for glasses or buttons. But my research is confined within the 17th and 18th century time period, focusing on inlay and veneer. When used as inlay or veneer, the substrate was often painted in a vermilion red, which, due to the translucent property of turtle shell, creates the luxurious deep red color that we see so often in furniture and cabinets. Now, there are two important things to know when it comes to understanding the biological structure of turtle shell, and particularly when attempting to identify the material. First of all, turtle shell is made out of keratin. Keratin is a structural protein that is the backbone of materials such as claws, beaks, horn, and even human nails and hair. And it is also the building block of turtle shell. Knowing turtle shell is made up of keratin is essential for infrared analysis, because keratin has a specific infrared absorbance spectrum, but more on that later. The second important thing to know is that the pigment creating the exotic pattern inside the shell is called melanin. Black melanin particles deposit themselves in tiny blood cells within the keratin matrix, clustering in groups that eventually create stains inside the shell, creating the natural aesthetically pleasing pattern that turtle shell is widely known for. In this simplified scheme, we can see the pigment distribution of melanin cells within turtle shell. What's important to understand is that the melanin cells cluster together in a high concentration to form the black spots, and that every one of the black spots that are present in the shell have a diffusion zone at the edge, where the melanin pigmented cells are still present, but in lower concentration, forming a kind of diffusion zone in between the transparent keratin matrix and the pigmented areas. This knowledge is essential when analyzing microscopic images of turtle shell. The final thing I want you to know before we move on to identification techniques is that throughout history, a lot of imitation techniques evolved to imitate the aesthetic qualities of turtle shell. My colleague Vadim van Meenen, who will be speaking after me, will go into more detail about some of these techniques. And for now, it is only important that you know that within 17th and 18th century Europe, the most common imitation techniques were transparent and colored varnish layers superimposed on one another on a red background, or by staining horn as a substitute material. As said earlier, horn is also made out of keratin, so it has the same biological properties as turtle shell. And therefore we question, are there accessible techniques to identify and distinguish genuine turtle shell from its counterfeit material? Now that you have a basic understanding of the biological structure and the characteristics of turtle shell, we move on to rather accessible identification techniques for the determination of the material. I will be focusing on two non-invasive and non-destructive techniques, optical microscopy and FTIR, or Fourier transform infrared spectroscopy. Both techniques take a different approach to the material and offer a good way for determination, but for more certainty, they are best used in combination with each other. Visual microscopy as an identification technique can be used to observe unique morphological structures, while infrared spectroscopy offers a method for identifying the chemical composition of the material. Both identification techniques were tested on two 17th century Flemish cabinets from the collection of the Royal Museum of Art and History in Brussels. Subsequently, the result of these techniques were compared to historical reconstructions of turtleshell imitations, which were conducted by my colleague Vadim van Meenen, who did his research about some of these imitation techniques. For the microscopical investigation, I used the Dynolight digital microscope, which offers a quite easy plug-and-play methodology and is importantly a non-invasive way to make microscopic images. Being a digital microscope, it is not necessary to go through the complex and invasive process of sampling, and it can be directly used on the surface of the object. Besides being non-invasive, this kind of digital microscope is relatively cheap in acquisition compared to a common stereo microscope. The only downside of using a digital microscope is that the maximum magnification is significantly less than with a stereo microscope. But I have found that for analyzing turtleshell, the magnification of the digital microscope was sufficient. Here we see two microscopic images that were taken from supposedly turtleshell veneer on one of the case study cabinets. What we see here is the transition from one of the black spots into the transparent keratin material. We can see clearly that the diffusion zone in between the black spot and the transparent material is present, and even the round melanin-induced cells are slightly visible, indicating that this is in fact genuine turtleshell. When we compare these images with images taken from known turtleshell, we clearly see similarities between the images. Especially the diffusion zone shows a likeness with the images taken from the case study cabinet. It is visible that the spots are made up of tiny round melanin-induced cells, indicating that the veneer in the cabinet is indeed turtleshell. Now, when we compare these images from the case study cabinet with images from shellac-based imitation techniques that were reconstructed by my colleague, we can see that in the reconstructions, the diffusion zone is absent, and that the transition between the black spots and the rest of the material is rather abruptly. Of course, we need to be aware of the fact that these reconstructions may not be of the same quality as imitations that were made by 17th and 18th century cabinet makers, and that historical imitations might better recreate a sort of diffusion zone in between the spots. It is still highly unlikely that even the original high-quality imitations were able to imitate the microscopic melanin-induced blood cells that are present in genuine turtleshell. If compared to microscopic images of horn imitation, the result becomes less clear. When we look at the front side of the imitations, where the spots were artificially added, we can see clearly that these are not genuine turtleshell spots. However, these horn-based imitations were probably used the other way around, with the spots facing the object. When looked upon this way, the result becomes less clear. The keratin-based properties of horn result in the same translucent, depth-creating structure that we see within turtleshell. The absence of a diffusion zone is the only indication that it is not genuine turtleshell, but due to the depth of the material, this is not as clearly visible as with varnish-based imitations. As we saw, microscopic images can be a good indicator for turtleshell, but it still heavily relies on the knowledge and experience of the observer, rather than offering a decisive determination. Therefore, a complementary analytical technique was implemented, called portable FTIR, or Fourier transform infrared spectroscopy. This technique allowed us to analyze the chemical composition of the sample materials and areas. With a portable infrared device, the goal was to analyze the turtleshell parts on the two 17th century case study cabinets from the Royal Museum of Art and History in Brussels. In order to analyze the data correctly, we first created a spectral reference database from turtleshell samples of correctly identified sea turtle specimen. For this, we collaborated with the Belgian Institute of Natural Sciences, where we sampled and analyzed 23 turtle shell samples from 3 different sea turtle species that were commonly used throughout the history of furniture making: the hawksbill sea turtle, the loggerhead sea turtle, and the green sea turtle. The primary goal was, as said, to create a spectral reference database of turtleshell, so we had a clear view of what an infrared spectrum of turtleshell looked like. Secondary, We wanted to see if it was possible to link the spectra from the case study cabinets to a certain species. Apart from the 23 turtle specimen we analyzed, we also wanted to analyze both varnish-based and horn-based imitations, so we could compare the analysis of the case study cabinets to each of these materials. The result of all these analysis was a standard spectrum of each of the three materials, which you can see here. The horizontal axis shows the wavelength of the infrared radiation, and the vertical axis shows the amount of infrared absorbance. Articles about the infrared analysis of turtleshell, like Espinosa's The Analysis of Sea Turtle and Bovid Keratin Artifacts, indicate that the important region for analyzing keratin-based materials lies within the 800 to 1750 region, which is around here. We can see that the varnish-based imitation, which is shellac-based, looks different than the other materials. But when we look at horn-based imitations, however, we can see that the spectrum shows a lot of similarities with turtleshell. This is due to the fact that horn and turtleshell are made up of keratin. So based on the visual comparative study of these spectra, and more specific of turtle and horn, there appears to be a little difference between the two materials. Yet the article of Espinosa, which I mentioned in the previous slide, showed that the statistical approach through principal component analysis, or PCA, and linear discriminant analysis, or LDA, proved to make a clear differentiation between keratin-based materials. So we used the data from our 23 turtle specimen to see whether we can identify the turtleshell species according to the PCA-LDA analysis. Although very preliminary results, we are willing to show it already. It looks like we can clearly distinguish three different groups representing each of the turtle species. Thus, it seems possible to differentiate between species with infrared analysis. Now we added the measurements from the cabinets, from the case study cabinets into the analysis in an attempt to see whether one or more measurements from the cabinet is classified to one of the three turtle species. Now, here, the gray dots on this slide represent all the measurements from the case study cabinets. We observe that these appear to be randomly scattered across the surface, all far away from the turtle and horn group. Hence, there appears to be no relationship between the spectra obtained from the cabinets with either horn or turtleshell. However, there does seem to be a differentiation between horn and the turtleshell groups, indicating that it should be possible to differentiate between the two, as Espinosa already had demonstrated. It only seems to be difficult to classify unknown material to either the horn or turtle group. There might be several reasons for this unsuccessful classification and observation. Most likely, it's possible that the portable infrared device didn't really measure the turtleshell veneer in the cabinets, but just measured the finishing layer on top of the turtleshell surface, hence showing no compositional resemblance to the keratin materials from our database. And secondly, the pre-treatment of the data could be faulty or too rigorous. This is still an ongoing investigation, and we will look further into the methodology and data treatment in the future to see if significant results can be obtained with infrared analysis. With this, we have arrived at the end of my presentation, and I want to thank you for your attention.
Thank you, Alex, for sharing and this insight into the identification of the real thing, which connects us so well to the next presentation. So I now have the honor to announce Vadim van Meenen, who was mentioned already twice, who is also a bachelor student from the University of Antwerp, and who will talk about the reconstruction of turtleshell imitation techniques on 17th and 18th century Flemish cabinets. So Vadim, please go ahead.
Good evening, everyone. Thank you for the introduction. Today, I want to present to you my research on turtleshell imitation techniques found in Dutch sources dating from the 17th and 18th centuries. My colleague Alex Verlinden told you about the structure and identification of a real turtleshell. Now we will focus on the imitations of this highly valued material. The aim of this research is to gain insight into the historical production methods and materials used to imitate turtleshell. Both our research is conducted under our bachelor dissertation, which we started in January 2022 and is still ongoing. First, I want to give you a brief overview about the use of turtleshell imitation in the 17th and 18th centuries. Sea turtle shell has long been used as a decorative material and cultural artifact for its unique appearance and pattern. Throughout the second half of the 17th century, the greatest cabinet makers used turtle shell in their elaborate marquetry. One of the most renowned figures in this craft was the Frenchman André Charles Boulle. He used this material as an inlay in conjunction with brass and pewter. This technique has become known as bullwork. Another object type where the exceptional beauty of the mottled and flame pattern of turtleshell is fully used are Flemish cabinets. The scutes of the turtleshell were laid on a ground of red vermilion mixed with animal glue, which serves as a binding medium and an adhesive. In doing so, the contrast between the pigmented and unpigmented transparent zones was enhanced. These luxury objects were mainly produced in Antwerp on a large scale and were exported to the European elite. They are characterized by the incorporation of a wide range of materials such as ebony, ivory, paintings, and of course, turtleshell. Throughout history, humans have always been fascinated by imitating the remarkable and curious creations of nature. The 17th and 18th centuries were a golden period for the art of counterfeiting precious materials with lacquer such as marble, ebony, lapis lazuli, and turtleshell. This was not only a matter of saving money on expensive materials. To produce things that were not what they seemed to be was a popular topic in the 17th century. It is not exactly clear when and why artisans started to imitate these materials, but in a fascinating article by Berit Müller about Baroque lacquer imitations, the author indicates that there is somehow a link with the introduction of the imitation of Asian lacquer. This started shortage of genuine Asian lacquerware due to its high demand on European markets. More readily available materials were used to imitate this lacquerware. This activity was called the art of Japanning and probably inspired artisans to counterfeit other exotic and costly materials based on the same principles of this technique. In the past, artisans have developed methods with various materials to imitate this highly appreciated material. The aim was to create a surface with the look and feel of genuine turtleshell without using the actual raw material. As my colleague Alex Verlinden mentioned earlier, there are two main types of turtleshell imitation in the 17th and 18th centuries. For this presentation, we will focus on these two different types. The first type was based on the traditional art of varnishing, whereby several layers of varnish were applied on a substrate to transform it into the aesthetic appearance of turtleshell. One of the earliest examples of this Baroque technique can be found at the Rosenberg Palace in Copenhagen. The framework in the bedchamber of King Christian IV was decorated with this type of imitation by the Dutch lacquermaster Francis de Bray in the 1660s. And the second type we will discuss includes the use of horn as a substitute for turtleshell by staining black or brown spots into the surface. This mimetic method was developed around 1600 and was well known by the Englishman John Osborne. Osborne was an artisan who was specialized in pressing animal materials such as horn and baleen using metal molds. So up until today, relatively little systematic research has been undertaken regarding the materials and production methods of these imitation techniques. The research question is, what were the known materials and techniques used to imitate turtleshell for 17th and 18th century Flemish cabinets? The aim of this research is gaining insight into the materials, techniques, and production processes of turtleshell imitation by means of reconstructing mock-ups based on 17th and 18th century Dutch recipes. Subsequently, we evaluated whether the recipes were able to imitate the material as accurate as possible. So to fully understand the production process, a number of mock-ups was made. For the period of the 17th and 18th centuries, we were able to find 9 Dutch recipes concerning these techniques. From these 9, we selected 5 for actual reconstruction. The authors have all their own procedures, with some providing more details than others. The selection of recipes for actual reconstruction was based on the descriptive clarity, safety, and feasibility of these reconstruction processes, and within the time available of the bachelor's dissertation. So 3 lacquer recipes were reconstructed from the authors Blankaert and Chomel, and 2 in which the staining of horn is described, written by Picterius and Thibault. Thibault's recipe from 1811 falls outside the scope, but was made anyway because it gives an alternative for nitric acid, the main product that was used for staining horn in this period. But nevertheless, this method was also described by English authors in the 18th century, like Dobson, Dossey, and Hodges. So please, per recipe, 2 different types of wood and substrate were used, beechwood and pearwood. Both wood types should be suitable for this technique, although pearwood is more close-grained and is therefore better suited for this application. The first step was to make the shellac varnish, which was needed for all 3 recipes. This varnish was to be used with or without additional pigments. After crushing the shellac into fine powder, it had to be dissolved in rectified spiritus vini, that is ethanol. To facilitate the dissolution process, the mixture was placed on a hot plate and heated at about 40 degrees Celsius. The solution was regularly stirred, and after 24 hours was it strained with a cotton cloth, after which it was ready for use. The oldest recipe, written by Blankaert in 1680, suggests preparing a white ground layer of lead white. The quantity of pigment is not mentioned in the recipe, so the pigment was prepared with a shellac varnish as binding medium by adding it until a desired color was obtained. So this manner of determining how much pigment is needed when no measurements are given is described by the German alchemist Johannes Kunkel as Augenmasse. He concluded that the visual evaluation based on empirical knowledge is decisive for determining the mixture's quantities, as none of this can be taught through textual descriptions on paper. So this colored varnish was to be applied in 3 layers, starting with a thin layer and ending with a thick layer. The next varnish consisted of the red ground. For this, the natural red resin dragon's blood was mixed with the shellac varnish. This colorant gave the varnish a reddish-orange appearance, which matched the color of the red ground used on real turtleshell inlay quite well. The black spots were then applied to bone black of charred sheep bone. For creating the pattern, I used this piece at the bottom of the slide as an example. Finally, the work was coated with several layers of shellac varnish and finished by polishing it with fine pumice powder. Chomel describes 2 different methods for imitating turtleshell with varnishes. The first method is much like Blankaert's description, except the pigment for the red ground is replaced by vermilion. Here, dragon's blood is used to make a ground layer for the turtleshell pattern on top of the vermilion ground. He probably suggests that this layer should function as an intermediate zone between the red ground and the black spots. At the top part of the mock-up, I tried to make the transition between black and red somewhat more diffuse. Once the varnish had dried, the work was overlaid with 8 layers of transparent shellac varnish and polished with pumice powder, followed by polishing with tin dioxide and olive oil. And the second method, described by Chomel, is more complex. He suggests to begin with an orange-colored ground, which is made by mixing pigments lead red and litharge with the shellac varnish as a binding medium. Contrary to the previous recipe, he also suggests to purify the dragon's blood varnish by filtering through a cloth. Chomel mentions to make clouds with the dragon's blood in which the orange partly has to shine through. The black spots were then applied with bone black mixed with the shellac varnish in several layers, whereby the surface was applied reduced with each stroke, resulting in a gradual darkening towards the center of the spot. Then a new varnish was made by dissolving shellac and sanderac with ethanol, serving as a transparent varnish that, according to Chomel, should give a better shine. Next, Chomel describes an interesting way to polish the surface. He suggests to use Dutch rushes or horsetail, a hollowed stemmed plant belonging to the genus Equisetum. It is useful because it contains a significant amount of silica in its cells and was thus used by cabinet makers to polish furniture. First, a bundle of dried Dutch rushes was made, with the tip slightly moistened in water. The tip was dipped into pumice powder, whereafter it was applied on a surface in circular motions. The result was a nicely flattened surface. So the next step was to provide the work with another 4 layers of shellac sanderac based varnish. The author suggests to apply these near a heat surface. He also notes that the source must not be too hot, as it may cause blistering on a surface. This was done by applying the varnish above a hot plate at a safe distance for the work. Finally, the whole was polished in the same manner as the previous recipe, with tin dioxide and olive oil until the surface showed a nice shine. So the next 2 recipes describe the imitation of turtle shell with horn or ivory. The use of ivory as a substitute in this context can be considered as an anomaly. Ivory mainly consists of hydroxyapatite, which is opaque white and strongly differs from the semi-transparent and thermoplastic nature of turtle shell's keratin. The manner of imitating turtle shell with ivory has not yet been found on art objects, so it could be a lack of knowledge of the author. But I will be very interested if anyone knows an object type with turtle shell imitation where ivory or even bone is used. If yes, please do contact me. For the reconstruction of Pictarius' recipe, a sheet of horn was used instead of ivory, since other authors, such as Kunkel, also described the same process using this material. The brown spots were stained on the horn with a solution of silver and aqua fortis, or nitric acid. Nitric acid has the ability to stain keratin yellow and should give a more brownish color if silver is added to the acid. The first step was to transfer 30 milliliters of nitric acid into a glass bottle. Then 7.5 grams of pure metallic silver was carefully added to the nitric acid. After 24 hours, the silver was dissolved. To create the turtle shell pattern, the horn was covered with several layers of beeswax, whereafter the spots were carved out with a spatula. The solution was added with drops into the openings of the beeswax layer. After 2 hours, a thin film on the solution could be observed, and the openings in the horn showed a slightly brown coloring. The dried solution, along with the beeswax, were carefully removed after 24 hours using a scalpel. The residual product can be best described as melted cheese on pizza. The spot had only some resemblance with real turtle shell when the work was turned on its back and held up against daylight. For the second horn staining recipe, other materials were needed. Thibault describes making a paste with quicklime, potash, and red lead, which had to be applied on the surface of the horn. According to Elizabeth Graal, the paste reacts with the sulfur in the horn to form black lead sulfide. Quicklime and red lead were mixed in the same ratio, whereafter a smaller amount of potash was added. Water was added until a consistency of yogurt was obtained. The paste was laid on the horn in such a manner to imitate the turtle shell pattern. After an hour, the paste was removed. So now I will discuss the results of the reconstructions, illustrated with cross-section schemes and an example of genuine turtle shell inlay. The colorants dragon's blood and bone black used in Blankaert's recipe match the colors of this example on the left of real turtle shell quite well. Furthermore, the transition between the black spots and the red ground is too abrupt, lacking the typical diffuse transition between the black spots and red ground, as we have seen with Alex's presentation. The use of vermilion as a red ground gives a more bright and deep red than dragon's blood. As with the previous recipe, the black spots do not flow into the red background. The problem with applying a varnish on a substrate is that the wet varnish tends to migrate to the edges of the surface, resulting in unwanted thickening at the edges. This could partly be removed by polishing the surface. Another way is to apply something I tried to do with the last lacquer recipe. The spots on the beechwood substrate look more like cow spots than turtleshell spots. The spots on the pearwood, however, are more successful, especially the zone at the top part of the work. The second recipe described by Chomel gives the best description of how the pattern must be applied. The structure of the pattern made on the beechwood substrate resembles the imitation at Rosenberg Palace in Copenhagen. The imitation by Francis de Bray is likely a solvent-based lacquer, possibly similar to Chomel's recipe. In conclusion, the lacquer imitation recipes describe a good way to imitate the turtleshell pattern, but the exact brightness and transparency of the real turtleshell scutes could not be obtained. And then the appearance of the horn imitations seem less artificial than the lacquer imitations. The spots that were made according to the recipe of Pictarius are less pronounced and are somewhat too light colored. Thibault's recipe, however, gave a better result due to the right color and depth of the spots. It must be taken into regard that the first reconstruction series I conducted was a process of trial and error, and therefore the not yet demonstrate the full potential of the recipes for imitating turtleshell. In context of this research phase, the process is prior to the results. The next step in this research is to make a second series of reconstructions. Here I will take my observations and new acquired knowledge in mind to try to imitate the turtleshell as perfect as possible. And thank you for your attention.
Thank you, Vadim, for an excellent and interesting presentation on your research, demonstrating that not all is as precious as it seems to be and how deceptive substitutes might have been produced. We now have a 15-minute question and answer session, and I can see that there were some questions in the chat box. And so let's start with our keynote speaker, Erma. Erma, can you please unmute your microphone?
Yeah, that's all.
Perfect. Thank you. The first question comes from Patrick, and he would like to know how long time did the scanning of the carved St. George sculpture take you? Or took you? Did you work in a team?
Yes, it was teamwork with a few people. One using the scanner, the handheld scanner, and the other one guiding it on the computer. The scanning is quite quick, so they scanned the sculpture in about a day. But what is really more time consuming is that you have to then sort of reconstruct the image with software. And that takes a lot more time, and you need to, get some experience with the software. I wanted to mention another method, photogrammetry, where you can use your phone to make lots of pictures. And there is a website called Sketchfab where you can get free software to then stitch all these images together in very nice 3D models. That you then have to put on their website, but you can also use. And more museums make 3D scans of objects now with that method and put them on the Sketchfab website with a logo from the museum. So have a look at that. It's a very nice way of making very nice 3D models of your objects. But it is ideally teamwork, because you need someone who can really use that software if you're not familiar with that, or with the scanner, the 3D scanner. Yes, really reconstruct the object with the software. Yeah.
Yeah. Thank you, and I agree completely. Well, the scanning is fast, but the work afterwards is time-consuming, especially if you do it for the first time. So
yes, exactly.
Yeah, but it's very interesting. Yeah. So we have another question from our colleague Andreas Cooper. He wants to know, what do you think about trying and exercising old manufacturing techniques in the light of the challenge to get appropriate materials and to deal with sometimes incomplete and hardly understandable information for historical sources? And I think I have the same question. So what do you think?
Yes.
And yeah.
Well, yeah, the reconstructions and remaking or reenactment methods are very, very much relevant for understanding the gaps in information. I think the last talk from Vadim showed beautiful reconstructions of recipes, and interestingly, they're quite varied, and combining the way these recipes work gives you already more and more information on how understanding these old methods. I think reconstructing many recipes, for example, in the research on smalt with those glass cakes, we collected a whole database full of recipes on smalt and extracted a sort of modern recipes for the reconstructions. And even then, we found during making smalt, which is a blue glass, so we did that in Portugal in a center for glass and ceramics at the university, new university in Lisbon, where they are specializing in that. Even then, we found that there were issues that didn't quite work. But by doing that and then trying to understand why, and talking to glassmakers who often have thorough knowledge of older methods, you slowly fill these gaps. And what we need to understand, I think, is that looking at all these recipes, they represent often either experiments, one-off, and then it works, and then they write it down, or they represent skills that have been built up over generations. But we don't know which one is which. So there's so many things for working with recipes and reconstructions that we need to keep into our minds. You can't take it at face value. You have to put it in context. You have to try and fill in the gaps. Talk to practitioners now and reconstruct all these old methods, and then slowly start to understand what you're looking at when you study these rare and precious materials, as has been shown very nicely in the last two talks, which I think are fantastic research. Yes.
Yeah, I think also it's always trial and error when it comes to that, and from that you learn, and from that you learn the most. Yeah,
true.
Slowly fill in the gaps. Yes. So thank you. Let's proceed to questions for the next speaker.
Yes, hello. I only have one question from Andreas Krupa. He asks, do aging processes of the investigated materials influence the FTYR results? And it's an excellent question, but one I can't decisively answer right now because we don't have sufficient data of aged samples. This is still an ongoing investigation, and it can be entirely possible that aging does have an effect on the infrared spectra of the materials, but further investigation and data are needed in order to analyze possible and sufficient differences.
I actually have a second question for you, which concerns the horn imitation. So the question was, did you show a technique to imitate horn, or did you show horn that was used to imitate turtle shell?
I showed horn that was used to imitate turtle shell. So the keratin material, it was horn, but the black spots, they were artificially added with the recipes from Vadim.
Okay. If I may add a question, I have a bit of horn that has black shading in it. Would you think that you could observe similar structures as you've shown in your images, in your microscopic images?
Yes, we did observe the natural stains that are present in horn material, and these show much more similarities between between turtle shell. So they do show similarities, but there are also some differences in the spots, in the natural spots of horn. They are the melanin is produced more linearly instead of in clusters. But yeah, they do look alike. But in horn, naturally, those spots aren't present the way they are present in turtle shell. In turtle shell, there are much more spots, and they are everywhere on the material. In horn, it is mostly just in one place, and it's the undersides of the horn.
That's very interesting to know. Good. There is another question just arriving.
Exactly. Maybe I asked.
Maybe you
I
asked
haven't
right
finished.
away, yeah.
Exactly. I'm just curious, do you really expect differences in the FTIR spectra of horn and turtle if both are made of keratin?
This the articles.
Well, it's just,
yeah.
Sorry.
The articles we read that already investigated the use of infrared analysis of both horn and turtle shell, they already talked about differences that were present, even though it is the same material. The thing is, when we talk about keratin, we are looking at certain amide groups, which are called amide 1, amide 2, and they are present in a certain region of the infrared wavelength. So what we do is when we look at keratin, we look at this certain region of amide 1, and it's present in between the 800 and the 1750 region. And in this region, the spectrum visually looks the same, but when you analyze it with artificial intelligence, the computer is able to find some differences in the data, because they are made up of different amide groups. They are both keratin, but horn and shell, they have a slight difference in the amide 1 group. I hope this answers your question a little bit.
Yes, perfect. Thank you.
Okay.
There is a comment in the chat box for Alex and Vadim, if you could get in touch with Erma about the technical art history project on turtle shell in objects in the 16th and 17th centuries. So that should be a good start for networking in your area.
Yes, we will try to contact through our promoter of the research, which is Vincent Kappersel. So we will look into this to contact each other.
Good, thank you. If there are no other questions, I would like to suggest that we proceed to questions for the next speaker.
Exactly. Thank you, Alex. Again, here are some questions for Vadim. Vadim, can you unmute your microphone, please? Perfect. So the first question comes from Andreas Cooper again. He would like to know, what sort of shellac have you used? Because there's so many different ones.
Yes, indeed. I used pure crushed shellac. But Blankaert, so the first author of the oldest recipe, also describes a process for preparing stick lag and purifying it with soap. But this was too time consuming for my bachelor dissertation. So I opted to use prepared shellac, or readily available shellac that I crushed in a fine powder.
Okay, thank you. Actually, my question is also about the shellac varnish. How did you apply the shellac varnish without re-affecting your imitation? Because you said several layers of varnish of shellac varnish was applied after your imitation. And how did you apply it without reactivating the paint, which is also, if I understood correctly, which was also bound with shellac?
Mm-hmm. Yes, so I applied the shellac varnish with a brush with like one quick stroke. Then I waited until it was dry. It was about 15 to 20 minutes. And then I repeated with a new layer, only one stroke. So I didn't dissolute the under shellac layer.
Yeah. Thank you. Perfect. Another question, which is from our colleague Sophie Guillaume. She would like to know, were you able to compare your reconstructions with turtleshell imitations from the 17th and 18th century? And if so, were you able to recognize the techniques?
Yes, so this is the next step in my bachelor dissertation. Now I focused mainly on the production process found in recipes, but we will conduct some analysis on art cabinets, Flemish art cabinets in the Museum of Brussels, the Royal Museum of Art and History, because we know there are some parts that are imitation, dating from the 19th century. So that is something we will do the coming weeks.
Okay. We are looking forward to hear the outcome of that. And there's another question of Alma Ben Youssef. She would like to know, did you use dragon's blood powder or resin lump? And did you notice discoloration, darkening, browning of the dragon's blood with time?
Yeah, so for the recipes I used dragon's blood in prepared powder. Even though there was a dragon's blood lump available, but as with the shellac varnish, it was a bit too time consuming to conduct the crushing of the lump. And yeah, indeed, I noticed discoloration because when I made the varnish, when I made the dragon's blood varnish with the shellac, it was very dark red in as a solution. But when I applied it, it was somewhat more orange colored. But then again, when dried and when more layers were added, it became more red. And it was like, yeah, red, orange color, but a nice color for turtle shell imitation.
Okay. Thank you. And there's another question, the final question so far here from Erma Hermens. She would like to know, do the recipes indicate how transparent or opaque paint layers should be?
No, that is not, it's not mentioned, no. Only, the only time it is mentioned that a varnish has to have a nice shine is at Chomel, and he says to prepare a finishing layer with shellac and sanderac, and that should give a better shine than shellac varnish alone. Yeah, so I hope that was an answer on your question.
Okay, thank you. So there are no more questions for you, Vadim, and
Thank you.
or if I haven't missed any, but I hope not. So thank you, Erma, Alex, and Vadim for this wonderful first part of this session. And thank you to your audience for the interesting questions. We will collect the remaining ones, or the ones I may have overlooked, and forward them to our speakers so they can have a look at them later. Now we're going to take a short break of 10 minutes. So get yourself a nice cup of tea or a beer or some cookies or chips, and see you in 10 minutes. So bye.
Welcome back, everyone. We hope you had a refreshing break and are ready for the second part. Its program looks as exciting as the first half, so first off is Johanna Haas with her poster pitch. Johanna is a bachelor student from the Cologne Institute of Conservation Science, and we will now hear about her work on a powder flask, a study into its manufacturing technique, art historical background, and conservation options. Go ahead, Johanna. Johanna, can you hear me?
Sorry.
Yeah, that's fine.
Hi. Okay, should I start?
Yes, please.
Yeah. Okay.
Whenever you're ready.
Good evening to you all. Thank you for letting me present my research tonight. I'm going to start by introducing my object and its damages, following with a rough overview of my research results regarding the manufacturing technique, art historical background, as well as provenance and dating. In the end, I'm going to try to point out the different possibilities for the restoration and reasons leading to our final concept. Okay. The powder flask belongs to the collection of the Cologne City Museum, and the round wooden body has a diameter around 11.5 centimeters. It's equipped with a brass spout tube and matching hinge closure, as well as 2 iron eyelets screwed into the side. The walnut body is decorated with a detailed work of inlays in geometrical forms made of bone, wood, and brass. The object is missing 2 important parts, a spring lock to keep the hinged closure on top of the spout tube, and some kind of middle part to close the annular body. At the moment, you can reach into the corpus through the hole, so it can no longer fulfill its purpose as a vessel. Due to climatic influences, the subsequent swelling and shrinking of the wooden body opened cracks around the eyelets and along the fiber in the corpus. Furthermore, several inlays on the back loosened and have fallen out, revealing the drilled holes, as you can see here on the right. As results of the turning process, rough grooves on the inside can be felt, so and viewed more closely with an endoscope, as you can see on the right. On the left this is an X-ray image of the powder flask, where you can see how thick the corpus is worked. In cooperations with 2 wood turners and a lecturer of mine, a reconstruction of the corpus was partly achieved. The hollowing of the body was not feasible because we missed some special tools, but the outside worked quite well. The damages of the inlays made tool marks, for example, from the center point of a drill bit visible, and the derived technique got tested on a flat walnut base. On the right here you see my trial panel. Both reconstructions led to a great appreciation of the high craftsmanship needed for such a fine worked object, especially to develop the hollowed body and the fine inlay work on an arched surface. The powder flask was a part of the standard equipment of a hunter. It was traditionally worn on the back or over the shoulder with the strap. in addition to a smaller bottle for the ignition herb that was carried on the chest. Without purpose-specific motives, like, for example, a hunting scene, any conclusions regarding the intended use, like for war or for hunting, cannot be made with certainty. The ring bed type, as you can see it here, with a round wooden corpus in combination with decorative elements made of metal and horn or ivory, is counted among the earliest types of powder flasks. A literature research led to several comparative objects with the same shape and similar decorations made of comparable materials such as ivory, bone, or mother of pearl, wood, and metal veins. This allowed narrowing down the dating and provenance to the German or Polish area in the late 16th to early 17th century. Here you can see my best comparatives objects. On the left, this is a couple of powder flasks that was sold at an auction house in Munich and was described as German from the middle 17th century. And on the right, this is an internet find that was assigned to the Polish Army Museum. Okay. The aim for the restoration measures was a cohesive and well-kept appearance to prepare the object for a possible exhibition. This means cleaning and consolidation of the whole object, as well as putting and retouching of the biggest cracks on the back. There's several ideas for the original form of the missing parts. You can see two examples here. In comparison to my object, the question arises whether and how the missing parts should be reconstructed in order to present a complete object to a future visitor of the exhibition. Together with the owner of the objects, we decided to not to reconstruct the missing parts because we were missing more information to narrow down and verify the original shape of the middle part and the spring lock for specifically this powder flask. You can see the middle part, for example, could have been in a ring shape or full, made of wood or some kind of bone and ivory. The original shape could be presented to a visitor by using, for example, pictures of comparative objects. Okay. So thank you all for listening. I'm excited for your questions and possible discussion of the reconstruction. Thank you.
Thank you, Johanna, for sharing this beauty of craftsmanship. We will get to the questions later. So our next speaker is Mair Trueman. Mair holds a BA in Egyptology from the University of Cambridge and is studying for an MA at the University of Amsterdam. The topic of her MA thesis and also the title of today's presentation is Craftwork of the Ages, a timeline of ancient Egyptian woodworking techniques. Mair, the stage is yours.
Thank you, and good evening to everyone. As you've just said, my talk is based on the research that I carried out for my 2020 master's thesis at the University of Lincoln, looking at woodworking techniques in ancient Egypt. So I will outline the general thesis work, but most of this presentation focuses on a case study from the thesis to highlight some of the key discussion points. For this, I'll do an overview of some major points of interest in the construction of several artifacts before a more in-depth look at comparisons between them and the conclusions that we might draw from this. So most of the work that I did for the thesis involved reviewing artifacts and the existing literature to identify woodworking techniques, working back to the earliest example of evidence for those techniques. I mapped these onto the accepted chronology of ancient Egypt to give a better indication of the earliest appearance of techniques and when variations can be seen to emerge. This is a huge topic which produced quite a long dissertation, hence I'm concentrating on the case study. This should give you an idea of some of the techniques encountered in my research and their application in one type of object. From this, we can more easily discuss two of the project's aims, as highlighted here, the characteristics of ancient Egyptian woodworking and the extent of change over time. The case study looked at changes in ship construction, comparing the construction as exemplified in 3 major finds: the early dynastic Abydos BG-10 boat, the Old Kingdom Khufu I ship, and the Middle Kingdom Dasha red and white boats. Now the map here shows the rough locations of the find sites, which vary according to the Royal Centre at the time. While the construction of these ships has been extensively studied by nautical archaeologists, particularly Ward, Lipke and Kriesman, direct comparisons placed within a chronological framework of technique development do not appear in the existing literature. You can see from this timeline that we're covering a long period, and although there is a large degree of consistency in tools and techniques, key differences in boat construction can be seen when we compare these objects. So to begin, BG-10 is a boat grave from Abydos, which was discovered in 1991. About 20% of it survived within a mud brick structure near the funeral monument of Khasachemwe. It's among the earliest recorded wooden boat burials, dating to around 2650 BC. You can see from the image that BG-10 has a flat-bottomed profile with an angular chine, by which I mean the change in direction where the flat base meets the side. The boat's plan and profile has been reconstructed from its overall measurements and the rising angle of its eastern end, showing it to be a long, narrow and shallow vessel suitable for river transport of about 22 metres long. BG-10 was built using an indigenous non-coniferous timber cut into planks of a uniform 6 centimetre thickness but of varying lengths. On this diagram, you can see the central timber labelled B3, this one here, provides the centre line for the hull. It was found to have the finest grain and fewest knots of all timbers used, a feature also seen in the central planks for the Khufu I and the Dasha vessels. All planks are straight-edged with no joggles or wood joints. So rather than using wood-to-wood fastenings, the planks were secured using a sewn construction technique. Channels for lashings were cut through the planks at various angles depending on their location in the hull, and transverse lashing across the width of the vessel provided lines of reinforcement and strengthening the hull. Moving on to the Khufu I, this was discovered in 1954. It was in a dismantled state inside a mud brick structure associated with the Pyramid of Khufu, placing it at around 2566 BC. It has been the subject of several reconstruction attempts and so has been extensively studied and recorded. Measuring 43.6 metres in length and built using cedar planks, the Khufu I vessel showcases many innovations in Egyptian boat construction. Between the hull, deck and the 3 deck houses, we see a wide range of woodworking and joinery techniques, some examples of which are listed on screen. You can immediately see that this cross-section is more complicated than that of BG-10, although the general shape is quite similar. The planks themselves are joggled to help distribute stresses around the hull, and the hull is built around a plank base composed of 8 enormous timbers, arranged in groups of 2, 3 and 3, and then joined end-to-end, aligned by exposed tenons. The hull planks are secured with 467 mortise and tenons, while deck beams are notched and lashed into the sheer straight beams, these longitudinal beams along the sides of the hull, and further supported by cross braces. The diagram also shows the use of batten seam construction, where the boat is kept watertight by tight planking and by using battens to cover the inboard face of the seams between planks, these battens here. You can also see from this cross-section that there has been a change in the lashing technique used between BG-10 and Khufu I. The BG-10 lashing channels, seen on the left here, made use of secret mortise lacing, while the Khufu I on the right uses mortise lacing. Secret mortise lacing provides the stronger joint as the lashing channel passes through 2 faces of the plank, while a mortise lacing channel only passes through a V-shaped groove in the top of the plank. Mortise lacing therefore requires the support of wooden joints to prevent planks from folding together. The key difference here is that the Khufu I lashing is not required to provide any real strength to the hull. It is used instead to support the wooden joinery and to fasten the seam battens. And finally, discovered in 1894, the red and white boats are 2 of 5 found outside Senwater III's pyramid at Dasha, dating the vessels to around 1839 BC. Both are roughly 10 metres long, the white boat shown on the left here being slightly larger, and like the Khufu I, they were built with cedar planks. From this plan for the white boat, we can immediately see a difference in the shape of the cross-section, with the base and sides curving into an inverted arch. It is now this arch shape that distributes stresses throughout the hull, using slightly wedge-shaped planks and keystone-like timbers at the bow and stern to create a hull in the shape of a tapering barrel bolt. This explains the lack of joggling in these dashur boats compared to the Khufu 1 vessel, which required the joggling to redistribute stress. The red boat here is very similar to the white, although with a slightly shallower silhouette. Hull strength for both is imparted by thick, edge-jointed planking with regularly spaced, deep mortise and tenons acting as small internal frames. The central plank is 10% thicker than the others and shows the highest frequency of mortise and tenons, providing longitudinal strength. Meanwhile, the beams, as seen here on the cross section, provide transverse strength, being attached to the planks below by large tree nails. The beams are supported from beneath by up to 3 anchored stanchions at the uprights in the cross-section. The dashur boat's construction appears to rely solely on wood joints and careful engineering, with limited evidence for lashing. But it should be noticed that traditional lashing techniques do continue to be seen in nautical contexts that are near contemporary with the dashur red and white boats. Timbers from Licht, dated to 1950 BC, show the same stitching technique as used on the BG-10, even displaying the same dimensions in the lashing channels and woven bands. These timbers also show the same joggling techniques as seen on the Khufu 1 vessel. The barrel vault hull of the dashur boats clearly demonstrates a development in the application of woodworking techniques, but at the same time, a high level of continuity and standardization can be observed in over 800 years of boat building practice. So now to consider some of the major discussion points from the thesis as illustrated by the case study, starting with characteristics of Egyptian woodworking. A notable feature of Egyptian woodworking is early technique innovations as seen in wooden shipbuilding and elsewhere. Placed in the context of the early dynastic period, we can use this to comment on some of the driving factors behind innovation, particularly social competition and environmental and economic forces. An increasingly hierarchical social system developed from the late pre-dynastic to the early dynastic periods, seen in the increasingly lavish burial goods, a major example of which is wooden boat burials. You can see from this image here the truly grand scale of the Khufu 1 ship and the great investment of materials that has gone into the ground here. In this way, social competition and a move towards more monumental materializations of dynastic power in Egypt may have helped to promote the rapid innovation in woodworking seen at the time. It certainly promoted more foreign trade for resources like cedar. In terms of economics, the importance of the Nile to the Egyptian way of life cannot be overstated, as the country's rich agricultural economy and formal route through a desert environment. So water transport and boat building technology was vital. Much evidence of boat building comes from ceremonial sites, but this type of object is in origin a mode of transport used for fishing, hunting, communications and trade from as early as the 4th millennium BC. The lashing techniques used in the construction of early boats enabled easy disassembly and assembly, allowing them to be transported overland when needed and allowing for stable constructions without the need for metal fixings and adhesives. These advantages promoted the migration of lashing techniques into many other types of wooden Egyptian artifacts. The objects produced by Egyptian woodworkers demonstrate a practical mindset, well adapted to deal with the properties and limitations of their working materials. This is exemplified in several features of early woodworking, such as a thorough understanding of the properties of wood, the use of relatively poor quality materials, even in high status contexts, and techniques for minimizing wastage. This practical approach allowed Egyptian craftsmen to work within the constraints imposed by poor native timbers. The piecemeal construction of a large proportion of wooden artifacts from Egypt clearly originates in a need to reduce waste and to compensate for poor quality timbers. Even with the expansion of foreign trade for better quality timber, the need to conserve such an expensive resource remained imperative. So, for example, in the dashur boats, at least 60% of the timber has been reused, as you can see here with multiple redundant mortises from previous uses. Meanwhile, it has recently been proposed that parts of the Khufu 1 were scavenged from another vessel, and that this is the reason parts of the reconstruction fit together poorly. Early evidence for workshop practices can be seen on BG-10, and the 2 surviving pieces of lashing that were found at the site consist of woven straps about 7.5 centimeters wide. These fit into channels that measure 8 by 2 centimeters which is equal to the ancient Egyptian measurement of 1 palm by 1 digit, providing evidence for its degree of standardization. From Khufu 1, there is a wealth of evidence for the process of assembly, with the carpenter's marks shown here used to orient parts to the builders. The images on the left show how adjoining planks are marked with twin hieroglyphs. Similar marks to those used to show which quarter of the ship each plank belonged to, as you can see on the right, can also be seen on other wooden constructions. I have observed them on Middle Kingdom coffins and early dynastic gaming pieces, providing more evidence for the longevity of craft traditions and standardization in workshop practice. There is a high degree of continuity in the types of techniques seen between early dynastic and later objects. The real change over time can be seen in the specific combinations of techniques. The vast majority of techniques used on the Khufu 1 and Da show boats are in evidence from the early dynastic and early Old Kingdom periods. But looking at the evolution of a single object type, as in this research, we can see changes in the deployment of these already established techniques. From the increasing complexity and number of techniques between the 2nd dynasty BG10 and 4th dynasty Khufu 1, to the growing sophistication and engineering ability applied to the 12th dynasty Da show red and white boats. Any river-worthy vessel relies on the redistribution of stresses from the forces encountered while in the water. The specific design features that allowed each of the ships to function can be seen to have changed from one to the next, even as the overall appearance remains fairly constant, all being long, narrow ships with a shallow cross-section. BG10 relies almost entirely on transverse lashing to strengthen the hull, while Khufu 1 combines this with wood joints, joggled scarf joints, and the creation of internal frameworks. The Da show boats show a more radical change, with the flat-bottomed and angular chine of the Old Kingdom vessels replaced with a U-shaped cross-section. This shaping, aided by wood joints, is responsible for the redistribution of stress. The application of technique therein displays advances in the engineering knowledge and technical ability of ancient boat builders, allowing them to produce simpler yet still effective designs. It's important to note that resource availability plays a large role in technique innovation and refinement, particularly the available wood species and tool technology. Copper tool technology develops in Egypt during the late pre-dynastic and early dynastic, and it is from this time that the first surviving ship burials are found, with tool marks on VG10 showing it to have been manufactured using metal tools. Although wooden boats can be made without metal tools, the development of metallurgy does allow for more precise woodworking and improves efficiency. Following on from this, Khufu 1 showcases the advancements that are possible with better quality timbers, with imported cedar allowing for a much larger ship, as cedar allows for larger, better quality planks than the native species. Following this again, the Da show boats postdate the advent of bronze tools in Egypt, and these stronger tools contributed to the precision of Egyptian woodworking in general, and some may also have had influences on ship design and manufacture during the Middle Kingdom. So to summarize, evidence from boat burials shows a high degree of continuity in tools and techniques used in shipbuilding, but we can also see innovations emerge, taking advantage of new materials becoming available or indicating developments in engineering abilities. Tool technology and resource availability are key factors in ancient woodworkers' capabilities and the potential for innovation. However, we can also see the restrictions imposed by poor quality and scarce native timbers help to drive adaptability, leading to the rapid development of a wide range of techniques as required to deal with these issues. This was a very quick look at a rather complicated subject, but I hope that I've given you a good impression of the great ingenuity of ancient craftsmen who, when faced with the difficulties presented by the quality of native wood and the expense of foreign timber, quickly established techniques that enabled them to construct large, complex and often beautiful wooden objects. I'd also just like to thank Henning as my supervisor for the thesis, for all his guidance throughout. And finally, here's a list of further resources on Egyptian boats and woodworking in general. Thank you for your attention, and do let me know if there are any questions.
Thank you, Mair, for this very interesting presentation and the insight into the developing early woodworking techniques in ancient Egypt. It was interesting to see that these these to be examined by an expert in both fields, and luckily also to learn that some things don't seem to have changed that much. So our next speaker is Emily McClain. Emily holds an MA in Arts Conservation from Queen's University in Canada, and will now talk about her research as Furniture Conservation Fellow at the Winterthur Museum in Delaware, where she has discovered that nothing is as it seems, investigations into a 17th century cask. Emily, over to you.
Hi. All right, I will be, as you said, presenting over the conservation of a 17th century American cask suspected to have been made in the New York area. This was a research project supported by a grant from the Americana Foundation, which made it possible for the project to take place at the Winterthur Museum, Garden, and Library in Wilmington, Delaware, in the United States. So here is a brief outline of what I will be discussing today, and you can see the cost that I will be discussing to the right. So as I said, for a brief overview of the project, this was a 6-month project in which I worked with senior furniture conservator Kathy Z. Gillis and curator of furniture Josh Lane. The goals were to perform an in-depth technical examination of the cost combined with literature research to determine the most likely original appearance of this cost, and if it was determined that the cost had been greatly altered from its original appearance, perform any necessary physical reconstructions to bring the cost back to its original appearance. So for a brief introduction to the form, Kosten are a variety of European cupboards which developed stylistically in the Netherlands with the growth of large freestanding case furniture emerging from medieval Europe. Kosten in the Dutch tradition are typically associated with the storage of clothes and household linens, and were often given as wedding dowries or gifts to newlywed couples. American-made Kosten, particularly in the New York area, were influenced by their Dutch predecessors, but developed their own styles owing to delayed exposure from fashions, traveling from the European continent, and the historic control of 17th century New York by both Dutch and English empires. American Kosten in the 17th century typically had 2-door cupboard units which were fit with interior shelves, and they may or may not have had a lower drawer unit. There are currently 5 known 17th century New York Kosten, which are shown here and are in various collections in the United States. The cost that I will be discussing is shown on the far left and is a part of the Winterthur collection. So the Kost under study was previously owned by the Hewlett family of Long Island from the 1650s to the 1930s, until it was acquired by H.F. DuPont for the Winterthur Museum collection. The Hewlett family immigrated from England and settled in New York around 1648. It's unclear if the Kost shown here was constructed in New York or if it was brought with the families from Europe. 2 historic sources, which are shown here, mention the Hewlett family and state that they brought a carved English oak cupboard or an old clothes press as they traveled from England. It is also possible that the Kost was introduced by the family of one of the wives who married into the early generations of the New York family, all of whom had English or Dutch ancestry. So as the project began, one of the first things concentrated on was the in-depth physical examination of the Kost in an attempt to determine the cultural origin of the Kost and to describe the overall appearance of the Kost. The Kost is a frame and panel construction made primarily of riven white oak. It has 2 large 6-paneled doors which rotate on iron pins set into the top and bottom of each door. The 6-panel door, as well as the vertical lapped clapboards, which form the back wall of the Kost, reflect Dutch housing construction techniques from the early 17th century. The clapboard backs can be seen on a number of the other 5 17th century New York Kost examples, and the 6-panel door structure can also be seen on the far right in the example from the Metropolitan Museum of Art. The Kost exterior is decorated with applied plaques to give the appearance of fielded panels and is decorated with an interesting vegetal inlay design on its 3 applied pilasters and 4 of its octagonal plaques. Inside, the Kost has 2 shelves and a large interior drawer unit, which also contains geometric inlay. The interior drawer unit is unusual due to its size and the inclusion of 3 drawers and its irregular construction. Few 17th century Coston contained interior drawer units, and if they did, they were typically much smaller, a single drawer, and they hung from an upper shelf. This drawer unit is constructed from reused oak and pine boards and is roughly joined to the Cost interior over the existing joints in the carcass. It almost appears as if it was a later addition to the Cost. While studying the Cost and comparing it to contemporary examples, many peculiarities became apparent, prompting further research and affecting treatment decisions. These anomalies were compiled in a list and included in the report appendix. The most influential anomalies included the large interior drawer unit, the inlay designs, and a number of newer cut red oak replacements seen in the cornice, the base moldings, and the feet, which had no previous documentation. The examination of the Cost was followed by scientific analysis in the form of ultraviolet photography, X-radiography, optical microscopy, XRF, FTIR, and PI-GCMS in order to inform treatment steps. But these methods will not be fully discussed here due to time restraints. Instead, I would like to discuss the treatment of the Cost, which can be broken into 2 parts. Part 1 being treatment steps carried out to inform the examination and documentation of the Cost, which included the disassembly of the drawer unit, wood identification, and the removal of certain decorations. And Part 2, which included treatment steps to return the Cost to its most likely original appearance. This included the cleaning of the Cost, both dry cleaning and solvent cleaning, and creating fills for missing design elements, and the reconstruction of the cornice, base, and feet of the Cost. So first, treatment was performed, as I said, to facilitate the examination and documentation of the Cost. The shelves of the interior drawer unit were disassembled and documented to gain a better understanding of the interior joinery and construction of the drawer unit. To the right, you can see the wooden rails which support the drawer unit and their peculiar joinery, which, as I said, overlaps and cuts into the existing joints of the main carcass. Next, several applied decorations were removed from the Cost using small wooden wedges in order to identify the wood or examine the decoration surfaces or the surface of the Cost underneath. Here you can see a discovery made during the removal of applied decorations. A hidden 3-petal inlay design was found underneath applied pyramidal decorations, which were situated in the corners of the octagonal plaques. Interestingly, the inlay was only discovered underneath 2 of 16 pyramid decorations. It was found underneath 2 decorations which were made of cedar and suspected to be original. Inlay was not found underneath the other 14 pyramid decorations, which are suspected to be later replacements as they are made of a different wood and have a different finish history. After the examination and photo documentation of these units, the drawer unit was replaced and removed decorations were reattached using existing nails, wooden pins, and if necessary, hide glue. The remaining treatment steps concentrated on returning the Cost to its most likely original appearance. The Cost was dry cleaned overall with a brush and vacuum through nylon stocking, and then areas of pilasters and octagonal plaques were selectively cleaned to improve the readability of obscured inlay designs due to darkened finish applied over heavy areas of dirt. Acetone and a following solution of 1% Triton XL80N and water was used to remove the darkened finish and the underlying dirt. Once cleaned, the pilasters and plaques were toned with pigmented paste wax in non-inlaid areas to promote the readability of the inlay, as the original appearance of the inlaid designs would have been including bright and contrasting woods. A before and after image of the cleaning and toning can be seen to the right. Distracting areas of missing inlay decoration were also filled with pigmented wax or with appropriately cut strips of ash wood toned with acrylic paint. An example of the wood fills can be seen at the bottom left. The final portion of the project involved the interpretation and research and examination to create digital mock-ups of the most likely original appearance of the Cost and to perform the necessary physical reconstructions to achieve this appearance. So, once fully examined, the joinery and constructions of the Winterthur Cost were compared to 17th and 18th century Coston and other collections. A library of pre-17th century through early 18th century Kosten from the New York region in the Netherlands and English cupboards was created from digitized collections available to the conservator and is shown on the right. The profiles of the cornices, base molding, and feet were examined to gather information about the design styles and construction practices of the Kosten and related 17th century forms. 32 examples were included in the library overall and were categorized according to the dominant profile features of the moldings and appearance of the feet. Due to the small sample size and inability for many of the Kosten to be viewed in person, this visual library was only cautiously used as a guide. Next, digital reconstructions of the likely original representation of the Kost were created, and examples of these can be shown in the bottom left. These digital reconstructions were created with Adobe Photoshop according to physical evidence found on the Kost and supporting literature resources. To begin, digital reconstructions were created to represent the Kost as it appeared in an image taken before the accession of the Kost, likely sometime between the 1930s and 1950s. However, this image was not dated, and when compared to other Kosten of the period, this design, which included a lack of feet and a simple cornice, did not reflect the extensive decoration of the Kost and did not seem likely. There were two important considerations which prompted us to move forward with the design of another Kosten. First, across the Kost, there is one dominant 3/4 inch tall molding profile, an ogee with two fillets, also called a kaima, which is shown to the right. This molding is found on the doors, the side panels of the Kost, the inset panels above the doors, a bottom row of dentils on the Kost, down the front stiles of the carcass frame, on the interior of the door, the clapboards along the back interior wall, the edge of a shelf, the applied moldings of the drawers, and the decorative railings above and below the drawers. As this profile is incorporated widely in the design of the Kost, and there is no inclusion of any other major profiles in the Kost, it seems likely that this molding or profile may have been included in the cornice or base molding of the original Kost design. Another important consideration was the lack of physical evidence regarding the attachment of the feet. This could be explained if the Kost at one time rested in a lower drawer unit. The common occurrence of lower drawer units underneath other Kosten and evidence that the interior drawer unit may have been a later addition suggests that the original design of the Kost may have included a lower drawer unit and featured the drawers from inside the Kost. Many digital mock-ups were created, but only the three most likely design configurations supported by analysis and research are shown here. I would like to focus my discussion on the process of designing the configuration shown at the top. This Kosten design incorporated the interior drawers with a lower drawer unit and included a cornice with a kaima recta profile, a lower base molding with an ovolo profile, and ball feet. Within the Kosten studied, there were two likely design configurations for feet: squashed ball feet or block feet, which were extensions of the styles. For this design, ball feet were selected due to the abundance of other Kosten examples with ball feet when they included lower drawer units and larger cornices. The cornice profile design shown to the right was based off of comparisons of the dominating profiles of other cornices within the Kosten library and the widely spread use of the kaima reversa or ogee profile across the cornice, or across the Kost. Within the library, the major cornice profile of nearly 2/3 of the Kosten sampled, including examples of Dutch, English, and American 17th century Kosten, were kaimas in the recta or reversa form. So it seems like a likely possibility that this profile was featured within the cornice of our Kost. The lower base molding was designed in a similar manner. Within the Kosten library and supporting research done by Kenny Safford and Vincent, ovolo profiles were found to be a dominant lower base molding profile on 17th century Kosten. Both Dutch Kosten and English cupboards of the 17th century included ovolo base moldings topped by small kaimas or cavettos, as this would incorporate the kaima molding already found across our Kost. A similar base molding design was created for our Kost and is shown to the right. The three most likely designs configurations arrived at during digital reconstruction are shown here, and these designs were selected by the curator Josh Lane and conservators Kathy Z. Gillis and Emily McClain to be discussed with a group of museum professionals familiar with Kosten at institutions such as the Metropolitan Museum of Art, the Art Institute of Chicago, the Rijksmuseum, the Victoria and Albert Museum, and also with private woodworkers. After discussion, it was the design shown at the top of the screen which was agreed upon as the most likely original appearance of the cost. So this design was selected to inform the physical reconstructions of the cost. However, during examination following the dissemination of these 3 digital representations, newly compiled evidence prompted the creation of a 4th design, which is shown on the left. Oxidation shadows and scribe lines on the existing architrave were reinterpreted to suggest a cornice profile with 3 projections above the pilasters. This is consistent with an early 17th century Dutch style, exemplified in this example of a cost from the Rijksmuseum collection as shown on the right. This final design was completed within the last few weeks of the project and so was not reshared with museum professionals due to time restraints. Instead, it was decided to commence with the final treatment steps of the project using this design. The final treatment steps of the project include the physical reconstruction of the cornice, base, and feet and are currently ongoing. This stage of the project is being completed with the help of Ken Sampson of the University of Delaware Art Conservation undergraduate program using white oak and materials from the Winterthur grounds. All replacements will be applied to the cost in an entirely reversible manner to allow the future study of the cost. The cost will rest in a new lower base unit and the cornice will be secured to the cost using existing holes from previous treatments. After the treatment, the current plans for the cost are to return it to a display in its previous exhibition location in the Oyster Bay Room of the Winterthur Museum. So I would like to thank you. That is the end of my presentation. And I would like to acknowledge everyone who has made my research possible.
Thank you, Emily. What an interesting research project, actually, and astonishing reconstruction. We now have a short Q&A session because it's already very late. Again, there are quite a few questions in the chat box. May I ask our speakers to turn on their microphones only when we address a question to you? Okay, so let's start with Johanna. Johanna, can you unmute your microphone, please?
Johanna, there are 2 questions for you. So first one is, did you have wood turning experience before attempting the reconstruction?
No, not at all. I only watched the reconstruction, actually. My lecturer had turning experience and did the reconstruction herself in our working space.
Okay, thank you. And the second question is, after seeing your slides of the object, the surface looked significantly darker where the inlay was missing. Can you say something about the surface treatment?
The surface treatment isn't really clear yet. We don't have any clear foul fluorescence or anything. The recesses are darker because they are still dirty. Now of cleaning the object, they are much lighter. Like, I don't know if you remember the smaller hole on the left side. So yeah, that's just because of the dirt.
Okay, thank you. So I haven't seen any more questions, so let's proceed to questions for the next speaker.
Yeah, thank you, Johanna. Now some questions for Mair. Mair, can you unmute your microphone, please?
Yes.
So, perfect. So the first questions from the audience comes from Tama Hessen-Grader. She says, thank you for this very interesting presentation, and she would like to know what the locally available wood species were and from where wood was being imported, since you've mentioned imported cedar.
Oh yes, well the native species, there are quite a few things like tamarisk, acacia, cedar, and then I think some fruiting trees like fig and olive. And then for trade, there was quite strong trade in the Mediterranean, particularly with Lebanon for cedar. And there's also some overland trade with Nubia, which is now Sudan, for ebony and many other precious materials.
Yeah, thank you. There's another question regarding the wood species. I had the similar question regarding the wood species. I was wondering if the same wood was used for dowels and planks, or it's the same wood used.
Yes, I'm not entirely sure. I think for the ships that they used the same wood, but I know in many other types of object, particularly coffins and furniture, they would use a harder wood for the dowels. But I'm not sure for the boats. I don't think there are different ones, at least not mentioned in the reports that I read.
Okay, thank you. There's a question from Vincent. He would like to know, was the hull or any part that is in direct contact with water protected by a coating?
Oh yes, I don't think on these ones there is some debate as to whether these boats were actually put to water because there isn't evidence for anything like that, and it's also things like the fact that some of the parts were scavenged from other vessels and it doesn't fit quite properly suggests that they were sort of put together in a bit of a rush because somebody had died sooner than expected. So for these boat burials, there doesn't seem to be anything like that. But for actual working vessels, there could be. I don't know of any surviving examples of working vessels, but it would make sense.
Okay, thank you. I hope this answers the question. Yeah. So then we have more of a comment from Elise Anderson. She is asking you if you are planning to go to the upcoming symposium Woodworking Tools and Techniques, Past, Present, Future. Welcome to bring a poster. Your subject would fit into the theme. She has sent the link also in the chat box, so you might think about going there.
Yes, thank you.
Bring up a poster. And then we have a final question from Sophie. Were the vessels used as ships before they used as burial vessels or made for that ceremonial purpose?
Oh yes, I think that's partly. Some of them might have been used, but it is thought that something like the Khufu one might have been made specifically to be buried because it was the issue of some parts of it not fitting properly in the reconstruction, thinking that they had been building it for burial and then run out of time, and so had to sort of grab other pieces so that they could put it in the ground.
Okay, thank you. I think we don't have any more questions for you, so let's proceed to questions for the next speaker.
Thank you, Mair. And now some questions for Emily. And there's one from Irene Menengeti. I hope I pronounced that correctly. Emily, what provoked you to remove the pyramid decoration? Did any of the analytical methods you mentioned show signs of the inlay underneath?
So we removed the pyramid decoration in order to do wood identification. We were able to visually identify that 2 of the 16 pyramids were made of a different wood species than the remaining 14. And so we visually identified them as cedar, but wanted to confirm this with analysis. So we removed the wood decorations, and it was actually upon cleaning the aged hide glue underneath the decoration to replace it that we found the inlay. We had previously done x-rays of the door panel which didn't show the inlay. It wasn't visible in any of the exposures that we had for the x-rays. So it was chance, I guess, in removing the aged adhesive.
Yeah, it's very interesting that you found the inlay exactly under those 2 which were different in wood. So thank you for your answer in that respect. So I don't see that there is another question. So these were the final questions for today.
Yeah, so thank you again, Johanna, Mair, and Emily. And if we overlooked some questions, we will mail you the leftover ones, definitely.
So this brings us to the end of the third ConNext session. I would like to thank again our keynote speaker, Erma Hermens, and a big thank you to all our speakers of today, Alex Verlinden, Vadim van Meenen, Johanna Haas, Mair Trueman, and Emily McClain. We would also like to thank our institutes and partners, and not least, thank you, the audience, for making this event happen. The next session on 2nd of May will be presented under the title Conversation. I knew that I would get stuck there. And we will start with the keynote speaker, Stephanie Offray from the Getty Conservation Institute. The session will be hosted by Friederike Wentig and Andreas Cooper from Cologne. So see you all next Monday, same time, same place. Bye.
Bye-bye.